But now I'd like to say something more about this thermal energy dissipation term. So if we go back for a moment to the dot product of the Cauchy equation with velocity, right here, equation number 2, you see this equation was this equation really gave us an equation for the rate of change of kinetic energy in terms of gravitational forces and surface forces. It would be nice if I can derive a kinetic energy equation which relates the change of kinetic energy to the work done by body forces, which is this term, and the work done by surface forces, which is not this term but rather is this term written up here. So I can do that by using the identity that I have here, and that's what we will do. So we use 3 in equation 2. So basically we replace the term in equation 2 using this identity, and what we will obtain is the following. Let me write it here on the side of the temperature equation, thermal energy equation for convenience. Sorry, my notepad is jumping around a bit. Okay, so what we have here is the material derivative of kinetic energy is equal to rho g dot the velocity plus the divergence of, let's go back to this equation, the divergence of T dot V minus T double dot T, because I am replacing using 3 and 2 of the stress tensor dot V minus T double dotted with E, which in turn is simply rho g dot V plus the divergence of T with V, where one can then use Newton's equation here, and then this term, as we've already seen, is 2 mu E double dotted with E. So one can use the Newton's constitutive law here to get a larger term, but my point is to focus now on this term. So you see that this term, which appears here with a negative sign, is the cause of the loss of kinetic energy. That same term appears in the thermal energy equation with a positive sign, increasing the temperature of the fluid. And this is why we call this term the thermal energy dissipation, or energy dissipation to heat. So what this equation tells me, let me write down the kinetic energy here. Yes. So this is the kinetic energy equation, let's say 7, energy equation. So what this equation tells me is that let's say I begin a fluid, I start with a fluid in motion, but then I do not exert any body or surface forces on it. What would happen is the fluid won't stay in motion forever, rather the velocity will keep decreasing because of the loss of kinetic energy due to this energy dissipation. And that kinetic energy which is lost due to the action of viscous forces will get converted to heat and show up in the temperature balance equation. And so it is because of this term that a fluid cannot keep flowing indefinitely without the application of a force, unless you have an inviscid perfect fluid, in which case there is no action of viscous forces and you will not have any generation of heat due to energy dissipation. So this one can clearly see here from these two terms. Alright, so that brings us to the end of our derivation of the thermal energy equation. But at this point now, before moving on to mass conservation, it would be nice to make a few statements about the meaning of pressure in the incompressible equation, since it also has some relationship with the thermal equation for temperature. So let's do that before moving on to the mechanical energy equation. So the meaning of pressure in an incompressible fluid. So why does this question arise? Based on the thermodynamics you already know, you know that the pressure in a fluid should be subject to change based on temperature and the volume of a given mass of fluid. Moreover, in order to determine the temperature, one needs to relate it to the specific volume and to determine the pressure, one needs to relate it to temperature and specific volume by an equation of state, like the ideal gas equation or van der Waals equation for a gas, or some other appropriate equation for a liquid, and so on. But you notice that when we write down the Navier-Stokes equations, we had fully specified the equations after applying Newton's law, Newton's constitutive equation. And so the pressure was already determined. Why? Because you had the continuity equation, divergence of V equal to 0, and you had the three components of the Navier-Stokes, the momentum balance equation. That's four equations. And your unknowns are the pressure and the three components of velocity, because you've written already the stress tensor in terms of the velocity gradient and the pressure. So your pressure and three components of velocity entirely determined by the continuity equation and the three components of the Navier-Stokes equations. And so the pressure is determined simply from the dynamics, and there is no place for it to be thermodynamically specified. And in fact, this makes sense because in an incompressible fluid, we essentially get rid of the necessity for an equation of state, and the pressure loses its thermodynamic meaning. Instead, it is simply a mechanical force quantity that in some sense arises from the necessity to maintain incompressibility of the liquid. So this is what we call mechanical pressure. Mechanical pressure. And one can define the mechanical pressure P, mechanical, which arises in the incompressible Navier-Stokes equations, to be simply the negative 1/3 of the trace of the deformation tensor or the velocity gradient tensor. It should be the trace of the stress tensor, because that's the tensor of surface forces. So you see from this definition, and you can check that this definition is consistent with Newton's law of viscosity, or the linear Stokesan constitutive equation. And so what this means is that the mechanical pressure can be interpreted as some mean squeezing force at every point in the fluid, and it has a purely mechanical interpretation and is not related to thermodynamics. On the other hand, if we deal with a compressible fluid, then you see that the continuity equation is in terms of now the density and the velocity. So it does not allow you to determine the pressure because you've made density an unknown. And therefore you need another equation to relate density to pressure. That's where we bring in an equation of state. But such an equation of state would typically also require you to know the temperature, which is why you need then the thermal energy equation, which I have written here above. Yes, equation number 5. And so for a compressible fluid, you need to solve typically the continuity equation in terms of density and velocity, the Navier-Stokes equations for a compressible fluid, along with an equation of state and the thermal equation for temperature in order to get a closed system. But once we say a fluid is compressible, we just have to solve continuity and Navier-Stokes, and one only solves the temperature if you want to know how the flow affects the distribution of temperature in a problem, or maybe in certain cases if the viscosity is dependent on the temperature, as it is, for example, in the flow of magma and the flow of ice. And we shall encounter such a problem later. Okay, so this discussion was just to clarify the meaning of pressure and to highlight the fact that the pressure of an incompressible fluid is merely a mechanical stress term and is not related to the thermodynamic pressure that we know from thermodynamics, which is governed by an equation of state. Alright, so with that, let us now move on to the last governing principle that we have to derive, the conservation of a species inside a fluid. We begin once again by saying that the rate of change of the total species in a material volume is given by the input flux due to molecular motions, that is what we know as diffusion, and the generation inside that moving control volume or loss, as the case may be, due to a chemical reaction. So let's write down that principle directly. So conservation of species, let's say with concentration C of x comma t. So this is the concentration field of some species within the fluid, of some solute, let's say, within the fluid. And so I can write directly in mathematical language the material derivative of the integral over the volume. So this is the concentration is, let's say, moles per unit volume of the given species dV, must be given by the flux over the area. So again, because I want to be input minus output, I need a negative sign here. The flux Q of, in this case, species, so I'll put QC to differentiate it from the thermal flux, dot N dA, this is over the surface of the material volume, plus any generation inside the volume due to a reaction. Right, so now I can again use Reynolds Transport theorem for an incompressible fluid. What would I obtain? I'll simply get, so I can directly use it now. You can see I can apply the divergence theorem to the surface integral, and then I can use the fact that Vm is arbitrary. Leads to the material derivative of concentration with time being given by the divergence of Q with a negative sign plus the volumetric rate of reaction. And now for a constitutive law, we will use Fick's law of diffusion, the analog of Fourier's law of heat conduction, which in turn is the analog, at least for unidirection motion, of Newton's law of viscosity. But remember that Newton's law of viscosity looks analogous to Fourier's law of heat conduction and Fick's law of diffusion only if we have unidirectional motion varying in one spatial direction, because only then it takes the form of a scalar constitutive equation. Otherwise, it's really a tensor. So yeah, here we have again Fick's law. I would put in quotes because it's just a constitutive equation, which in our terms would be simply that the concentration flux vector, sorry I forgot the subscript C, is given, so basically the flux of concentration at every point occurs from a down gradient, so from high concentration regions to low concentration regions, and then we have a diffusivity of the species in front of it. So D is the diffusion constant, and so using this we obtain the material derivative of concentration is given by, again I'm going to, if I assume D to be varying in space, I should keep it inside the divergence, but if I can take it to be a constant, I can pull it out and write D Laplacian of C plus the rate of generation. Right, so this is the conservation of species equation that we were after. Alright, so that derivation is quite simple, especially in comparison to what we had derived previously. But now is an appropriate time to compare our equations. So let's look at this equation alongside now the temperature equation that we have on top. So let me write that down as well. So I'm just reproducing what we had written earlier. Alpha square theta, this is a case where thermal conductivity being a constant comes into this thermal diffusion term, plus here there is a source due to viscous dissipation, which remember is Cp E double dotted with E. And then of course we have the Navier-Stokes equations. This is the kinematic viscosity, but then now of course we also have a pressure gradient source term, and in general we'll have action due to gravity. Oh sorry, I don't have the density now, and this is pressure over normalized by the constant density. And this of course should be supplemented by the fact that the divergence of the velocity is zero, the equation due to of continuity. So that's it. Here, succinctly written, is the full set of governing equations that we're going to use in the rest of our course, of course in various simplified forms for various different situations. Now what I'd like to point out is that the source of the analogous nature of the transport of species, or what we call mass transfer, the transport of energy or heat transfer, and that what by analogy one would be tempted to call the transport of momentum. This analogy arises from the fact that you see all the terms on the left hand side, the convective terms of concentration, temperature and velocity have the same form. Of course here we would have to apply it to each component of velocity. Then the diffusive effects, whose origins are non-continuum in nature, associated with molecular motions, which have to be modeled by constitutive laws. All of these have the same diffusive form, at least in the case of a incompressible Newtonian fluid. And so one can speak about certainly the diffusion of a species, which makes total sense. In analogy, one can talk about the diffusion of heat, which has similar origins for an ideal gas. And finally, we have the diffusion of momentum. However, the diffusion of momentum can be thought of as being diffusive strictly only for an ideal gas where the molecules actually diffuse around and transport heat and transport momentum in this manner. But this is not generally true for other fluids where the stresses interact through bonds and other molecular forces. But nevertheless, mathematically speaking, at the continuum level, it has a similar structure, and this term really does lead to a sort of diffusion of, let's say, a momentum of velocity from regions of high velocity to regions of low velocity. And so in some special cases, especially unidirectional flows, where one can combine, where the pressure gradient is constant and it can be taken as a constant source term, one can then write down the momentum equation in a way that looks very analogous to the thermal equation, which looks analogous to a concentration equation. But these are really ultimately special cases, because you see that there are other terms in the equation which can change the nature of the equation dramatically. You have this extra source term that couples the flow to the temperature equation in a way that it is not coupled to the concentration equation in general. You also have the case where pressure need not be a constant applied pressure, in which case it could really be a function of space that is determined dynamically by the incompressibility condition, which enters separately. And in that case, then the momentum equation, or the Navier-Stokes equation, takes on a fundamentally different nature from the thermal and concentration equations. Finally, and most glaringly, the major difference between the Navier-Stokes equations or momentum transfer from the other equations is the fact that this substantial derivative or material derivative of velocity is nonlinear only in the momentum equation. Why do I say that? Well, if you expand it out, ddt, remember, of the velocity is rho v dou t. That's a linear term in the velocity. But then you have v dot the gradient of the changing quantity, which in this case is the velocity itself. So this term is strongly nonlinear. On the other hand, if you have ddt of temperature or concentration, this term is entirely linear in the transported quantity, be it concentration or the scalar concentration or the scalar temperature. And therefore, Yes, this equation is linear. So therefore, it's much more complex to solve the Navier-Stokes because it's this nonlinear term that gives rise to instability and multiple possible solutions. As we saw, if you remember in one of the early lectures, where we saw the example of Taylor-Couette flow between concentric cylinders, and in that case you saw a sequence of instabilities leading to a sequence of transitions in the nature of the flow. All the while you actually had a laminar flow solution that could solve the equations, but clearly that was not the solution you saw in the laboratory experiment because it becomes unstable for large flow rates. And this sort of behavior is all due to the nonlinearity of the equation. Whereas if the velocity field is specified, the thermal equation and the concentration equation is linear and it has a solution once and for all, and the issues of instabilities do not arise in that context. The same nonlinear term via instabilities and so on can lead to a strong multi-scale nature and chaotic solutions. That is, solutions which are aperiodic but bounded and appear random, and in their extreme version it's basically what we call turbulence. So all of the richness of transport phenomena in a sense really is due to the nonlinear term in the Navier-Stokes, and this nonlinearity in the Navier-Stokes leads to complexity in flow, which then of course impacts the distribution of the temperature field and the concentration field. And this is what makes transport phenomena a rich and vibrant subject. On the other hand, there are some cases where one can neglect this material derivative. Basically, this derivative represents acceleration or the influence of inertia. So for the flows which are very slow, you can neglect this term. Or in other words, the nonlinear term, which is the product of v with v itself, can be dropped if v is very small. This loose statement can be made more precise once we look at non-dimensionalization and scaling, which gives us a systematic way to decide when to neglect terms in the equations. But for now, consider that this can be done for slow flows, what are called Stokes flows, in which case you can neglect the time derivative, the material derivative of velocity from the equations. The equations then become linear. So for very slow flows, you have linear equations, and then you have only unique solutions. However, you could still have nonlinearity due to coupling with either the temperature or the concentration equation, let's say through the value of the kinematic viscosity. So to give you an example, consider the case of magma flows. Now if you've seen a movie of magma flowing, or if you look back to the pictures I showed in the first lecture, you'll notice that magma in fact flows extremely slowly. And so it really is what one would call a Stokes flow, and you can neglect this material derivative of velocity. So the equation of velocity may seem linear at first glance. However, the viscosity of magma is a strong function of temperature, and it becomes increasingly viscous as the magma cools. Therefore, this kinematic viscosity is a function of theta, but theta itself is a function of the velocity, both through the energy dissipation term as well as due to the convective terms in the material derivative. And so you have a kind of coupling between the equations, which is itself nonlinear because the dependent variables multiply themselves. So you don't have velocity multiplying velocity, but velocity multiplies temperature and temperature multiplies velocity. And so this sort of nonlinear coupling can also give rise to instabilities and complex dynamics. And we shall hopefully take up one such coupled heat and flow transport problems later on in the course. So with that, we come to the end of our series of lectures which looked at derivation of the governing equations. We now have the full set of governing equations before us. This is all we will need for the rest of the course. However, having said that, you can see that the equations are partial differential equations. They are multi-component vectorial equations, and they can be quite complex to solve in general. But what we shall do, and what is the main purpose of this course, is to see how we can apply these equations to specific problems, to take advantage of the specific nature of the problem of interest to simplify these equations to a form that ultimately is amenable to analytical solution or to solution by simple numerics, and that will ultimately allow us to understand the physics of the problem rather than just brute force attempting to simulate those equations. At the same time, in addition to providing now a foundation for the rest of our course, which will be based on analytical methods and simplified solutions, this sequence of lectures should also help you to understand the underpinnings of CFD or computational fluid dynamics software, which you might encounter both in if you do higher studies as research, or even in the industry where you might be using softwares like ANSYS, Fluent, COMSOL, and so on. All these softwares are based on these governing partial differential equations, and so it becomes important to understand the source of these terms, what their physical meaning means, and when you can simplify them, and under what conditions it would be required, let's say, to solve the full set of equations. When can you make simplifications? Under what would be the implications of assuming incompressibility, and what features you would lose, and so on. So in this sense, I think these foundational lectures would be helpful in a more general context as well. Alright, so with that we leave off and conclude this lecture, and from the next class onwards we shall begin looking at the techniques such as scaling and perturbation methods, which form the bread and butter of the analysis of transport problems. Thank you, and see you next time.